Welcome back. Today we're going to be looking at graphing functions by plotting points. This is where you take the x and the y that we talked about last week, the input and the output, and we throw them on a graph and see what it looks like, what that relationship turns into. So before we get started, thank you for being here. We're going to say our classroom creed. Remember, it's cool to say the creed. You know what's not cool? Failing pre-cal. You know what is cool? Learning, saying the creed, getting good test grades. So let's get started right after this. Today is a new day. I can read and remember well. I can develop my viewpoint and apply it correctly. I have eyes to see, ears to hear, and a mind to understand. It might not be easy, but it's worth it. Let's get started. So we're going to be looking at graphs of functions. Make myself smaller, throw myself in the corner, and let's get started. So the graph of a function, we've got this real definition. We've got the set definition where we build it into a set that says the graph of a function is the set of ordered pairs, the set of x, y's that look like this. X, comma, f of x, where x is in the set A, which A is the domain of f. So, that's a lot of long words for saying, hey, if we've got a domain of a function, we've got all of the what can x be's of a function, then we're going to plug them into the function, get all the y's for those x's, and make some points out of that. Now, you might have 3 points. You might have an infinite number of points, but that's what we're going to be looking at today and seeing the difference between the two. So let's look first at 3 quick examples. The first one is a lovely generic example. This is just, hey, if you've got a function, x comma f of x, and you've got some numbers, 1, 2, and then the random number x. This x right here, this is the coolest thing to look at, because this purple x right here could be any number. It could have been right here, and it would have talked about this point. That anytime you see that x, it's just a generic number anywhere on the graph. So we're looking at that, and we're looking at what happens when that x moves over. So it looks like it goes up for a little bit, then it peaks, and then it goes back down. Okay, cool. So this is just a function. I'm going to label all 3 of these. This is a function, f of x. Do I know that function? No, I don't know it. Looks like a quarter of a downward parabola, but could be a sine wave cut off. We don't know that function. You don't need to know that function. All you need to know, if you plug in 1, you get whatever value this is. If you plug in 2, you get whatever value this is. If you plug in x, you get whatever value that is. And that's all that tells us. No more, no less. So if we were to talk about it in class and say, what does this graph tell us? We can't be super specific, but we can say a few things. This next one, we can be a whole lot more specific. This one we can look at and we can say, well, this looks like no matter what x is, I'm going to get the same exact y. This is a cool function, a special function. It's a horizontal line, but this is this is always called the constant function. Constant function. All right. And this function is constantly 3. No matter what you plug in for x, you get 3. F of 1, 3. F of 2, 3. F of 3, 3. And so on forever. A lot of times people will do this thing where they'll write H-O-Y. Hoy. And it kind of stands for horizontal. 0, which we'll talk about later when we get to slope. I don't know why I made that then be set. 0 stands for 0. And y, because that line hits the y. That line hits the y-axis, so it's going to have the form of y equals something, some number. In this case, it's 3, but it could be y equals some random number. And that's the constant function. Okay, then we're going to move on, and we're going to look at, oh, sweet, we've got a linear function. And you know the linear function obviously just comes from the word line. So we got ourselves a linear function here. We've got the definition of that linear function with inputs and outputs. So if I input 1, let's just do that real fast. 2 times 1 plus 1. Guess what I better get? Looks like 3 on the graph, but let's check it and see. 2 times 1 is 2, plus 1 is 3. Check. That looks good to me. That graph, the x hits the y of 3, and the x of 1, perfect. I bet if you check that for every single point, it would work out. Now here's an important note to look at when you're looking at these graphs. How many points are on these graphs? Well, on these 3, infinite points. There's a billion million points. You could check 1, 2, 3, 4, but then you could go and check 0.1, 0.2, 0.3, 0.4. You can go and check 0.01. You can go and check 0.001. You're going to be checking an infinite number of points forever. So it's better to define it as a function instead of define it as a set of points, right? All right, let's keep going. Sketch the graphs of the following functions. And I should make this note. without a calculator. You don't need a calculator because you've got your brain, you got your pencil, you can write it down. You don't need no calculator to graph these. All right, let's see what happens. So we're going to start with just picking any points. Now, I would pick points that are on the graph given. Like, let's start with 1. We can pick 1 and plug it in. If you plug in 1 into that, guess what you get? 1 squared, which is 1. Cool. So what point does that make? Well, that makes the point x comma f of x, which is just 1 comma 1. Maybe I'll write it out to the side right here real small. And we can plot that point. What happens if we try negative 1? Negative 1 gives us negative 1 times negative 1 is 1. So that gives us this point, 1 comma negative 1. Or negative 1 comma 1. Oh, I skipped 0. Let's try out 0, see what happens. Plug 0 in. What's 0 squared? 0. Give us a point right there. All right. So we look like we got some sort of turnaround happening. What else? Let's try 2. 2 gives us 4. Negative 2 gives us 4. All right, I can do that. Looks like I got some sort of V shape happening. Not too crazy. You want to get the curve right. Maybe we try 1/2. 1/2 probably gives us 1/4. Negative 1/2 probably gives us negative 1/4. Oh, no, it doesn't. Fix me. Negative 1/2 squared is just the same as 1/4. So that'll zoom in a little bit, and that'll end up being like right here. Make it a little flatter. And we got ourselves one of the classicest parabolas I've ever seen. All right? Not too wild. So all we did is pick some points, and I think we even picked different points than the book does. Exact same example that's in your book if you want to look at it. But pick whatever points you want. Pick the hardest points, pick the easiest points. It doesn't matter. You're going to be able to graph your function by picking a point, plugging it into the input, and getting an output, and then graphing that point. Cool? All right. We're not doing B. You're doing B on your own. We're not doing C. You're doing C on your own. Though I will make a quick note while you work C, and then you can bring it to class if you have a question. Note, the square root is only going to yield positive results. Only positive results. So I know some people have been thinking about the square and saying like, oh, but if it's squared, can't we do plus or minus? Well, when the square root's happening, it's square rooting a positive number, and it's only going to yield positive results. If we wanted to flip it and yield negative results, we'd make a different function that had a negative sign out front. Cool? So as you're graphing that, to keep it a function, we're looking at the positive side of that graph. A lot of people make that mistake and try to do both, and it's like, no. We would define it if we wanted to do both. All right, so let's look at the second type of function called a piecewise function. If you want to review piecewise functions and plug and chug of all that, check the college algebra class. There is a section with that in it, but we're going to move pretty fast and do the exact same thing. We're going to make a little table. Even though I didn't give you one on this graph, you can make your own little table and plug and chug with that. So let's do it. We got an x and we got an f of x, right? All right, let's start with the lowest number way to the left of the top piecewise section. So let's start with, I don't know, negative 2. If I plug in negative 2, what do I get? Am I going to plug it in the top or the bottom? Well, negative 2 is technically less than or equal to 1 because it's to the left of it on a regular number line. So negative 2 squared gives me 4. So I'm going to go and plot the point negative 2 comma 4. All right, I'm going to do these all in different colors so we can see the whole graph, which is pretty sweet. So let's check 1. 1 is technically less than or equal to 1 because it's equal to 1. So we're going to be left with 1 squared, which is 1. All right, so we've got our red point, 1, 1. And if we know x squared because we just graphed it, that's a parabola. I'm going to go ahead and graph the rest of that parabola. Making a real important note in my brain that because that line... Oh, that was negative 1. Nah, we got to go all the way over to 1. My bad. Boop. Let's check negative 1. Negative 1, I'll do this one in green. Negative 1 yields 1. Put that over there. Purple. 0 yields 0. Put that there. Now I'm drawing my line. And I've got a sweet little parabola that we literally just graphed a second ago. And it goes on forever up. But here's something interesting. If we look at the end where it ends, does that parabola or does that x squared include 1 or not include 1? Well, because we're looking at the top function, it has the line under the inequality. We're going to definitely include the 1 and draw a big closed circle right there. which means our other line, because it doesn't have the inequality, it's probably going to have the open circle. So we're going to start with this linear function, and we're just going to plug and chug. Let's plug 1 in and see what happens. So now, if we plug 1 into the bottom function, we're going to get 1 yields us 2 times 1 is 1 plus 1 is 2. Oh, they're not even going to meet. They're going to be separated right there, right? It's actually 3. 2 times 1 is 2 plus 1 is 3. So we're going to hop up to 1 comma 3 and graph it with an open circle because it doesn't include it. The parabola included. The linear function did not include. And then we're just going to go up with a slope of 2. So it's probably going to be, let's plug in 2 and we'll be done. 2. 2 times 2 is 4 plus 1 is 5. 2 yields us 5. So if we go to 2, we'll go all the way up to where 5 should be and draw ourselves a nice line like that. Boom, done, sketched. Awesome. If you have any questions or you're like, I don't know how piecewise functions work, come to office hours. We'll work on piecewise functions. I promise. All right, let's see what happens next. Graph the absolute value function. All right, absolute value function is pretty much just a piecewise function that's a real specific case. If you don't remember it from a long time ago, like 9th grade, 10th grade math, we can skip ahead and just say we know it looks like this. I don't know exactly where or when or what place it's at, but I do know it's going to be like that sharp turn. So we're going to look at this absolute value. Let's see if we break it down as a piecewise or not. Yeah, we're going to break it into a piecewise function because it can always be written as that. So f of x, technically, if x is greater than 0, it's just the normal line. It's the normalest function in the world. So we're just going to say it's x if x is greater than or equal to 0. And then if it's less than 0, you know, the absolute value tells you the distance from the thing. So it's like, hey, we got to get rid of that negative sign. So it's negative x if x is less than 0. And that's the way we always write the piecewise absolute value. If there was some stuff happening to x, we'd have to move it over first, but there's not, so we're just writing the piecewise. So, boom. And then we're just going to graph that just like we did. So if we graph the top thing, I can leave you to fill in your table because I trust in you to fill in that table with 1s and 0s and see what happens. But as you work through it, you see you get a dot on the 0, 0, and you work your way up one step at a time, all the way up. And then we'll do the same thing going this way, and they do happen to meet at the same point, which is great. That means it's a continuous function. And now, is it smooth? Does it not? It has a sharp curve, so that's going to be tough when we get into calculus, but it is important to know that's a continuous function. It doesn't have any gaps like the last one. All right, absolute value. So we've got some piecewise, some absolute, we've got some parabola happening, some linear earlier. Now we got this cool thing called a step function. All right, let's look at the greatest integer function. So the greatest integer function, basically, it's like a step function, and it tells us, hey, we're gonna look at the greatest integer that's less than or equal to the x I give you. And there's like 100 examples right here. So if you look at this greatest integer, what is the greatest integer less than or equal to x? Or equal to 2? Well, it's 2. Greatest integer less than or equal to 2.3? Well, greatest, but less than 2.3 is probably going to be 2 as well. But then we take one little tiny step below, and it turns into 1, right? So we're always just shifting down just a little bit. And then there's this interesting case where we've got ourselves some negative numbers, and we've got to remember we're shifting down. Not in distance from 0, but an actual number. We're shifting down, down, down the number line. Cool? So let's pick some random numbers that are on this graph. What happens if x equals, I don't know, 1? If x equals 1, what's the greatest integer? Well, we just, oh no, it's not up there. The greatest integer less than or equal to 1, probably 1, right? So we've got ourselves the point 1, comma 1. Boop. But now let's do like 0.5, because that's going to help us know where this line goes. Well, what's the greatest integer less than or equal to 0.5? Probably 0. So that gives us that point down there. So if I'm just looking at this, it kind of looks like a line, right? But I think I got to be more careful. Let's try 0.99999 and a billion nines, right? Well, what's the greatest integer that's less than or equal to that? Not 1, because 1's greater than, so we got to go back to 0. So as we get super close, we still stay on that line, right? But then once we get to the 1, that can't be graphed on this line right here. I'll make it red. So we got to open it up right there. So we're going to open it up, and we're going to say, you know what's going to take care of that dot? Probably that point up there, and we're going to work ourselves over. And if you graph all these points on this function, you would probably see that on the left, we fill it in because it's less than. It's on the less than side. And on the right, we leave it open because it's going to step up, and it's going to go up one more. So it's going to look like this all the way up. That's kind of why it's called a step function, because you can see it looks like it steps up, and it really goes on forever and ever just like that. Now we could look at another function called the least integer function, or the lowest integer function, which you can kind of imagine to just move the line over a little bit and then kind of look at things that are bigger than or greater than or equal to that x. But if we see that in the homework, that'd be awesome. We could work it in class, office hours, whatever. Weird function, we don't see it a whole lot, but it's good to know I can graph it. If you give me the definition of a function, I can graph it. All right, and then I think this is the last thing we're going to, yeah, it is. Last thing we're going to talk about is this vertical line test. Vertical line test is one of the easiest and hardest things that kids work on all the time, because they're like, oh, I can do that, that's easy. But then when they get to knowing why it's true, it gets crazy. So if we're looking at the vertical line test for a function, and we're saying, okay, I've heard this since the 9th grade, that if a vertical line passes and it hits it twice, so if my arm's going across the function and then the function hits it here and here, not a function, right? So for example, this red vertical line only hits that blue line once. Check, it's a function, yay. This red vertical line hits that blue line twice. 1, 2, boom, boom. 2 times equals bad, not a function, right? So why is that? Why can't it be a function if it hits it twice? And that's the thinking question for the week. You come to class, you got that answer real solid, and it's a good, succinct answer, extra credit, promise. So the question to ask yourself and to think about, I'm not going to explain it here, is why the vertical line test matters, why it counts, why it makes your algebra life a billion times easier. And then we can just look at some examples like these just to make sure we know what we're doing, make sure we've got it down. So which of these graphs below represent a function? And all we're going to do is fill in that red line and say, yes, yay or nay. Well, hits it twice? No. Not function. Pretty easy, right? Yay or nay on this one? Oh, they don't even give us the red line. We got to pick it. So where do you put the red line? Wherever you want to. Or you can draw a million of them and see if any of them hit. Any of those lines, if it just moves its way all the way across, hit? No way. Watch this. I bet I could do one of these things. Goes away. That. Oh, nope. Never mind. Not worth it. So let's check this one. Ooh, this one's a little trickier because it kind of looks like it goes pretty steep. Any of these vertical lines hit? It doesn't look like it. So that's going to be a function too. I'm just going to write yes to save some time. Check. Check. Oh, and they give us the answer here. They drew a line for us. Does that hit? How many times does that hit? That hits 1, 2, 3 times. 3 times. Bad. So that is not function. Pretty cool? All right, so there's this quick review at the end of the chapter where it says, hey, here's some functions we've talked about. Here's some that you probably have seen before but don't remember. Look at these. You don't have to memorize them yet. We're going to hit them all as the year goes on. But it is important to see them and know, like, okay, I need to be familiar with these. If these come up again, I'm going to want to know that I have this chart to go back and look at to remember. What kind of function is this? And if you don't believe the function, we can zoom in real big, take that x to the 4th right there, and graph it on your own. Graph 0, -1, 1, and see what happens with those functions. Just like the way we did it before. But these are some of the most basic functions we're going to be using in this whole class. And they're going to help us with pre-calc as we move on. So, don't forget. Work those problems that we skipped on this one. Go check out the suggested homework and work on some of the suggested tips. Don't forget to do your actual homework, and I'll see you in class. Hopefully you'll bring some good questions so we can talk about some good mathematics. All right, see you later.